Hi, my name is Davis Railsback, and I'll be presenting to you our paper, Privacy Preserving Training of Decision Trees over Continuous Data. I'm a PhD student at UW-T, and I am working with a group of students and faculty out of UW-T and Monash University. Okay, so supervised machine learning is all about training models on historical data that can be used to make predictions on future data. So for instance, predicting whether a patient who just tested positive for COVID will develop long-term complications. So in this circumstance, having more training data is usually going to make more accurate models. So the more data that can be ascertained, the better. However, the training data, especially with medical stuff like this, is often kept in silos that are controlled by entities like hospitals who are not allowed to disclose the data to each other because of privacy laws like HIPAA. So a subfield of PPML which we're concerned with is all about developing MPC protocols to train ML models on this type of combined data or augmented data sets that are distributed between entities that are not able to disclose their data in the clear. Okay, so within this setting, we focus on decision trees because they're still the most widely deployed machine learning models in industry. That's a quote from Pedro Domingos in 2016. So in terms of actual application and being employed on these data sets in question that are siloed, it seems like a pretty reasonable thing. In the clear, decision trees are induced from a top-down algorithm that selects the features and puts them into internal nodes. And in the case of real-valued data, it also selects the query thresholds for those nodes. So the optimal candidates for splitting are selected based on a sorting algorithm, and in MPC sorting is quite expensive. So our work kind of comes in to figure out how can we solve the same problem, potentially throwing out the C4.5 algorithm, which is the one that uses this sorting technique, and achieve similar results with non-sorting based methods. So concretely what we contribute in this paper is a novel subset selection protocol, which is a method by which we convert the entire data set into random subsets that can be used to train trees within an ensemble. As I referenced above, we have a discretization protocol that we convert into MPC for turning real value data into categorical data. And to our knowledge, this is the fastest implementation of decision tree training on real features that currently exists in the literature. Okay, so next we'll just breeze through some MPC preliminaries. So we use additive two-party secret sharing. So in this situation you can imagine two parties, Alice and Bob, each have two secret values, and they would like to compute some function on the combination of those two values. So they encrypt them by each generating a number at random, and then taking the difference between that number and their original secret value. And then by keeping one of these and distributing the other one to the other party, each of them will have two numbers that appear random that add up to the original secret value. So just by virtue of modular arithmetic, the two parties are able to compute sums of two secrets, sums of secrets and constants, and multiplying a scalar by a secret. However, in order to compute multiplication of two secret values, we use beaver triples, which is an element of correlated randomness that allows an extra one-time pad of each of the secret values, along with a factor that is able to convert the multiplication into the other local operations that we're already able to do. So I mentioned that we are operating in the two-party scenario. So the two-party honest but curious setting is basically such that both of the two players cannot deviate from the protocol at all. They can just sit there and try to learn as much information as they want. And this is basically the weakest security setting possible, but it does make sense when legal repercussions are a good enough deterrent against deviating from the protocol. For instance, if protecting the data isn't the absolute key priority, but the chance that somebody got caught would be enough to deter them from that action. So this is actually not a restrictive security setting. So in the simplest case, we can imagine that Alice and Bob are directly computing on their own data, getting correlated randomness from a trusted initializer, but just the same way, any number of parties can also send secret shares of their individual data to both Alice and Bob, who then just operate an MPC protocol on their behalf. Finally, in the security setting, we can eliminate the trusted initializer entirely by splitting the protocol execution into an online and offline phase. And this simulating of the trusted initializer just kind of costs extra time and resources, but it's not required to include a trusted initializer. Alright, so now we're ready to discuss the actual protocols that we propose in this paper. So the first of the two is called random forests, and it's a pretty standard method for training ensembles of trees over categorical data. So the first phase is to select a number of trees that we want to train, and then split out that many random subsets of the data set using replacement on both the columns and features. And then for each of the subsets, we discretize the columns into some number of categorical variables, and then for each of those we learn a tree with ID 3. The second method does not discretize, and instead we compute the same random subsets that we do for random forests, and then instead of using ID 3 straight up on categorical variables, we use a modified version where at each node, when we need to determine the splitting threshold, we instead pick a random value between the min and max of each feature and use that as the threshold. And then the idea is that by having enough of those random thresholds will be close to the ideal one in the average case. So looking at these two algorithms then in the context of MPC, the things that are going to take a long time are this comparison between, or comparisons required to find the minimum and max values of vectors, which is needed both for the extra trees learning algorithm and then also for discretization. And then the other thing is going to be computing the subsets that are used for training each tree. So figuring out how to do that obliviously is going to be time consuming. So it's worthwhile looking into how we can optimize both of these protocols. So in each case we heavily use this idea of reusing correlated randomness. So we know that a beaver triple is a one-use only object, but it's worth reminding ourselves of why that's the case. So if you have two numbers being multiplied together with respect to one beaver triple, and then you take two different numbers and you multiply them together, in the phase of one-time padding the two secret values and revealing them to each other, both parties are going to learn enough information to derive the difference between the two operands. So clearly that's insecure. However, if it's baked into the protocol that one operand isn't going to change, like we need to compute the product between x and y prime, and the protocol itself specifies that x doesn't change between those two operations, then it only needs to be masked once, so only one u value is required. And so you can imagine that as the number of these y's increases and x stays the same, what we're doing is that in the moment of execution in the online phase, the number of triples that are actually being sent across the network is approaching 50% of what it would be if you aren't reusing triples here. So using this fact, we attempt to build protocols that reuse operands as much as possible. So applying this idea to random subset selection, we start with a data set that's m by n, and then we define a random feature selection matrix that is n times n prime, where n prime is the number of features we want in the subset, and we randomly sample these indices of the initial attribute, and we use those as the columns of this matrix. So computing one subset would be the product between the original data set and this matrix. However, if we zoom out to compute all of the tree subsets at once, then we can reuse the randomness that was applied to the data set against every random feature selection matrix. So the beaver triples that are actually required are 1 over t for the u value of what we would expect. Similarly, for comparison protocols which are required for the min-max finding, bit decomposition is the essential component of that, converting additive secret shares into bit vectors of secret shares over which integer logic is possible. So this particular architecture that we propose is intentionally designed so that at each layer the fewest number of operands are reused, where each node where two values are being paired up, that's representing a 2x2 matrix multiplication to compute the carry bit in a look-ahead adder. So if we do this naively, the number of multiplications required are going to be L log L, but in this particular architecture and making sure that we're reusing correlated randomness where possible, it reduces it to this complex expression over here. But in the case of 128-bit integers, which is what we use for our ring, it corresponds to a 40% reduction in data transfer size. So in terms of what this got us, you can see that for the protocol min-max here, which is finding the minimum and maximum element over a vector of some length, we're able to get the minimum and maximum of a 1,000,000-bit vector in less than 2 seconds, which is pretty surprising to us, and then extending that to discretization over an entire data set with 1,000 features. You can see here that if we split into only 2 bins, then even for 100,000 number of instances in that data set, it's still less than 2 minutes to discretize that entire data set. As for the top level protocols, the left side of this is showing in the clear accuracy results, and then the right side is showing our secure protocol execution. So you can see that there's a little bit of an accuracy drop between in the clear and the secure protocol execution, which is to be expected. These values can be tuned, such as the number of bins that are used or the number of trees that are used to increase that accuracy. But you can see here that the execution time for any of these is still measured in seconds, and with the data set sizes of 15,000 or so features, it's pretty clear that this is extensible to real size data sets. So as for comparison with contemporary work, there was a paper that was being published around the same time as ours that was taking a new approach to the C4.5 sorting-based algorithm that used three-party computation sorting-based networks. So we took their data set dimensions that they tested against, in which they report 28 hours for computing 200 trees with 11 features and 8,192 instances. And our protocol is able to execute in 8 minutes. So as a disclaimer, this comparison isn't 100% fair, because if they're using 3PC, the multiplication protocol itself is different. However, I think the difference is staggering enough that it's pretty clear if their protocol was implemented in 2PC or ours was implemented in 3PC, that we would be able to see still a multiple orders of magnitude difference. Another difference is that they do not randomly compute the subsets, or they're not using an oblivious protocol for that, and we are. Okay, so wrapping up, some of the takeaways are that shallow ensembles seem to work well with MPC's constraints, and so by virtue of, instead of training one large decision tree, which requires a lot of waiting for communication rounds and things like that, training a lot of shallow trees can yield similar results, even better a lot of the time, and it works well with the constraints that are imposed by secure multiplication. So, as we've shown empirically, discretization, or using categorical training of some type with ID3, seems to be more practical than C4.5 for secure training, though since we are losing a little bit of information in discretizing, it might be less accurate if hyperparameters aren't chosen correctly. And of interest outside of this paper, I think that just a general design practice of trying to reuse operands as much as possible will bring things out of the realm of theoretical and into the realm of practical a lot more quickly than other things. And if you would like to use our current primitives that I showed on the other slide, then feel free to check out our MPC library here, which is called Rustlinks. And as a separate note about those protocols, we're currently at a point where 70% of the time spent on a protocol is local computation and 30% is network. And this is a really kind of unheard of problem to have in MPC, because it basically means that now standard operations for optimization are going to be able to reduce the running time of these protocols even further, such as implementing GPUs for matrix multiplication and the like. So thank you, and I'm happy to take any questions.